Good morning, good afternoon, wherever you may be. My name is Anthony Price. I'm the Vice Chair of the Regional Advisory Committee for European SEG. And today I have the great pleasure of introducing Professor Martin Landro from the NTNU, who's the Director of the Center of Geophysical Forecasting. His list of accolades is very long, many awards. I won't go into too much detail now. I'm going to hand over to Martin to tell us today about the application of distributed acoustic sensing in geoscience and beyond. Thank you, Martin.
Thank you very much, Anthony. So welcome to this webinar. A few words about the Center for Geophysical Forecasting. It consists of 4 departments at NTNU. 12 industrial partners, including oil companies, contractors, but also governmental companies like NVE, etc. We have 2 research partners, which is NORSAR and Acoustic in Japan. We plan to educate 24 PhDs and postdocs over a period of 8 years. So this whole project lasts for 8 years. It started in 2020. So it ends in 2028. We have divided it into 7 work packages. And of course, work package 1 is the one I will discuss most today, which is about distributed acoustic sensing. And then work package 2, I will briefly touch on. It's about CO2 storage and energy storage. Also, work package 3 about monitoring and time-lapse. I will touch upon that. And then geohazard prediction is another topic together with NORSAR. And then we have 2, VP5 and VP6 are generic and within computer science and mathematics. And then this last work package is on deep earth imaging. Short about the whole concept of distributed acoustic sensing. It starts with an interrogator that you see in the middle to the top of this figure, schematic figure. It's essentially a laser source and a computer. So the laser sends a light beam into a fiber. And if the fiber is exposed to any kind of say, acoustic pressure or something that stretches the fiber, then that stretch in the fiber or compression in the fiber can be detected since small inhomogeneities in the fiber will slightly move, and we can measure that in the backscattered light in the interrogator. So that is kind of illustrated in the upper right here, where we cross-correlate 2 backscattered signals, and we measure a time delay or a phase change. So this technique we have used for several applications, geophysical applications, and also biophysical applications that I will discuss today. It's not fully true that we always measure a strain in the fiber. It can also be a temperature change, since what we measure is the phase change, and the phase change can be due to strain, as we see on this upper formula here, delta L over L. But the fiber itself, the glass in the fiber, might also change, the refraction index. And that can be caused, for instance, by a temperature change, as it's shown in the lower equation here. And that a temperature change can also directly lead to a strain change, but also a change in the refraction index, dNdt. And it turns out that that C term here is often dominant. So we measure actually a change in the velocity of the glass fiber itself. And that can be used to measure temperature. And I will show one example of that. This is from a well at the Johan Sverdrup field in North Sea. So we see this is a well that has been closed down, and then it's warming up again. So it's warmed up by the surrounding rock. So you see the cool colors here is bluish or darker. And the upper plot shows the DTS data, and the lower plot shows the dust data. DTS is in this content, we look upon that as the correct answer. So we see a temperature change here in that perforation interval of approximately 20-30 meters. But it's heating up from 77 degrees up to 85 degrees at the end here, over a period of 18 days. And to the lower plot here, we look at the dust data, which has been filtered to low frequencies. And we see a similar behavior, that we see a clear change in the phase measured by the interrogator. And we see how it's fading out over this 18 days period. So that is discussed in this paper by Nick Bradley et al. This is a more detailed plot showing a production example, where we see the median low frequency dust data, which is essentially the phase change response, as a function of depth in the well, and also as a function of time. And then if you integrate this over depth, you get this, the middle plot here, which shows the temperature change as a function of depth and time. And please note that the blue color here actually means a higher temperature, so it's a bit special color bar here. To the right, you see a comparison again between dust data and the DTS data. And what is intriguing here is that it seems like the dust data is picking up some of the minor temperature changes in this well. So it's pretty close to the DTS data. Then last year in 2022, we acquired dust data on a horizontal streamer, or fiber, I mean, dust of fiber. And we shot conventional seismic data above the same location. So to the right, on the plot to the right here, you see conventional streamer data. And to the left here, you see the dust data acquired at the fiber optic cable that is at the seabed. So this is work done by Bachrach et al. And presented in Geophysics. So there are two papers about this test that we did. It's one by Raknes et al. And one by Bachrach et al., which is more focused on data processing and imaging. So the major point with this is that it's similar, the dust data, but also different. If you start to look at details, you'll see differences. It's so promising, I would say, that this is something that we should consider, for instance, and it has been discussed for a long time, for monitoring of CO2 sequestration. So that's this plot that I borrowed from my colleague Phil Ringrose. So in the future, if we are going to reach, say, gigaton CO2 storage, which is what we hope we will see in some 10, 20 years from now, then we think that to use DOS, as is illustrated in this figure to the right here, both in well and also at the surface, it could be a spiral or any kind of fiber path that we choose on the surface. We think it's a very realistic alternative to more conventional PRM systems, for instance. So when we have to minimize the cost, then maybe fiber optic cables is a good alternative compared to conventional PRM systems or streamer data. Then I want to show you some examples we have done within the center over the last 2 years. There's a fairly long list, so I hope I have time to go through everything, but if not, I will stop at some place. One of the first examples we did was quickclay monitoring across the fjord from our university. Here you see from the trenching of the fiber, we dig the fiber down at approximately 40 centimeters. And this is from the control room where we place the interrogator and splice the fibers. This is from the construction. They built a new road in this area, and this is an area which there were a major quickclay avalanche back in 1978. 5 farms was washed into the sea, as you see here. So it was a big thing back in that time. And you see that the new road is kind of crossing this quickclay area. And we wanted to monitor what was going on, if we could see any changes in the shear wave velocity or the shear stiffness during the construction work. This is the result. So to the left here, you see hammer shots made at the well. The well is 20 meters, so it's just a small blue area in the middle here. But then when you see the strong events from the shot here, that is when it's on the surface. So most of this distance along the cable here is where it's on the surface, but then there is 20 meters for the well that is bluish more here. Then you see here on 12th of August that there is a person walking along the fiber, and it's very easy to detect that person on the data. So this is RMS plot. And then you see the background noise in the middle plot, and on the right-hand plot you see that when they started the construction of the road, which was maybe 50 to 100 meters away, we get a strong signal from the trucks, from all this equipment there. And again, you see the blue in the middle is the well. So the fiber goes into the well, to the bottom of the well, and then up again. Then on the right-hand side here, we can see what we were interested in. We wanted to measure changes in the shear wave velocity, and we used dispersion analysis to do that. So on the active hammer shots, we got 4 modes that could be easily identified, that you see here. And on the passive data, or using only the background noise, we got only the lowest mode, as we see here in plot D. The good thing about this is that we didn't observe any major changes in the data. So the conclusion is that we couldn't see any changes in the shear wave velocity during this almost 8-9 months period during the construction work. This is just another way of looking at it, where we have been a bit more detail on the shear wave velocity versus depth. You can see here it corresponds to 250 meters per second at the depth of 10-15 meters. So here we have compared linearized inversion and nonlinear inversion methods. So it's essentially the same data, but more detailed. Then I jump to Spitsbergen or Svalbard. In 2015, Norway decided that they needed a high-speed communication cable between Ny Ålesund, which is a research station up here. Approximately 40 to 50 people live up in Ny Ålesund on the north. It's almost 79 degrees north, as you see. And to connect that to Longyearbyen, which is the capital on Svalbard, maybe 2,500 inhabitants here. The stretch here is approximately 260 kilometers, and 2 cables were actually deployed at that time in 2015, paid by the Norwegian government, as I said, and the purpose was for communication, telecommunication between the 2 sites. On the bottom here, you see the depth profile going from from Longyearbyen at this side, all the way up to Ny Ålesund for the two cables, the black and the blue one. So we figured out that we could use this for sensing, and we entered into a cooperation with SICT, ASN, University of Bergen, Norway and NTNU, and we did quite a huge experiment in 2022 where we used 4 interrogators. 2 interrogators were placed in Ny Ålesund and 2 interrogators were placed in Longyearbyen. And to the upper on this slide, you see an earthquake. There are several earthquakes per day in this area due to the mid-Atlantic ridges out to the left here, to the west side. And this is a typical earthquake where you see the P wave arrival coming in here, and you also see the shear wave arrival coming in a bit later. So, and this shows all together 260 kilometers, where we have spliced, so we see a small white line in the middle here. That is approximately at 130 kilometers. And we have used one interrogator from one side and another interrogator and spliced them and mirrored them. So what you see here is a good example of the signal to noise ratio, which is good up to say 100 kilometers, and then you see around 130 kilometers. You see you can maybe follow the shear wave arrival, but the P arrival is kind of drowning. So it's a nice way to check your data quality and your signal to noise ratio. So we would say that in practice we can use maybe 100 kilometers of this fiber for analysis and so on. This is an example of an earthquake, and on the movie to the right now, you see when you get white colors, that's when the shear wave arrival is coming in, and you see this is real time. So you see how the shear wave arrival is now propagating from this 100 kilometers and closer to the Longyearbyen where the interrogator is sitting. So you see this white thing is moving, and now it's kind of hitting Longyearbyen there. And to the left you see the same data as normal seismic data, where you have the P arrival and you have the shear arrival here. And this we can then use to estimate or locate the earthquake. And this is a comparison between our estimate, which is the white star here, and the estimates done by Norway in red and the University of Bergen in orange here. And the three, it's hard to say which one is correct, but they agree pretty much. They are not too different. So, but the interesting thing, of course, about using a DAS fiber is that you have essentially a long antenna, and if the earthquake, which is shown as a red dot here, is not too far away, then of course you can use this antenna to localize the earthquake quite precisely, I would say, because you have an antenna that is of the same magnitude as the distance to the earthquake. This is a teleseismic earthquake, the Turkey 6th of February earthquake. What is interesting here is, first of all, we see it very clearly. On the horizontal axis here, it's distance from in Ny Ålesund. So the first 5 kilometers here is when it passes, the fiber is on land. And then you have at approximately 5 kilometers, it enters into water. And then when you see the P arrival is very strong, it's where you have sediments. So for instance, at 20 kilometers here, you see a pretty strong P wave event coming from the earthquake in Turkey. And then you have the shear wave arrival, which is also observed as a weak event on land, as you see. And then the surface arrival is later, and there you see stronger events on the land sensors, or when the fiber is on land. So to the right here, you see this as a normal seismogram. Then we also use the fiber to detect ships. So to the upper left here, you see the red line is AIS coordinates of a cargo vessel, Ålesund, that sails from Ny Ålesund to Longyearbyen, and the white dots is the acoustic positioning done if you rely only on the fiber. So the fiber is now the black line here. It's 87 kilometers, and the water depth here is around 300 meters, as you see. The signal, the raw signal, is shown to the lower left, where you see the hyperbolas, and those hyperbolas are used then to estimate the positions. In the middle, here you see the spectrogram, where you see distinct frequencies around 35, 45, 55, etc. hertz. You can even observe a Doppler effect, as you see on the plot C here. And the shift, the Doppler shift, although it's a bit noisy, is around 0.1 hertz. And if you know that, if you measure that, you can estimate the velocity, of course. To the right, you see wave signals. So these are at 37 kilometers here. You see blue whale signals as beautiful hyperbolas. And by doing beam steering on these signals, you can essentially calculate the acoustic signal of the wave. And if I press here, let me see. So this is a blue whale that is at 37 kilometers from Longyearbyen. And it's possible to kind of reproduce the acoustic toning, the acoustic signal from this blue whale. We have multiplied the frequency by a factor of, I think it was 2.5 or something, to make it more hearable to our human ear. So you see here on the spectrogram in the middle, in plot E here, you see how this sweeps going from 40 hertz up to 70 hertz and then down again to 30 hertz. How that looks like. And this is quite typical for the Atlantic blue whale. Then in red, it's the other whale that is some kilometers away. It's probably a fin whale. It's a shorter signal and a down sweep only, as you see in the spectrogram here. So this was the first time I think we have used a fiber optic cable buried 1 meter below seabed to reconstruct the acoustic sound of whales, and that was published in this in Frontier Marine Science. And we even made seismic data out of this. If you take the blue whale signal and use it as you use cross correlation essentially, or interferometric methods. The length of the signal is 4 or 5 seconds, and if you cross correlate that, you can make seismic shots as is shown here. So to the left, it's a seismic shot made by a blue whale at approximately 25 kilometers from Longyearbyen. We see the direct arrival. We see a reflection from the subsurface around maybe 200 milliseconds later. That's the orange line here. We see the multiple of the direct arrival. That's the dashed red line here. And we see the multiple of the first reflection as the orange line down here. We can also estimate, if we look at the frequency versus distance, we can look at the notches. And then these notches, the white lines here, they correspond to an assumed source depth of 20 meters. So of course we don't know the exact depth of the blue whale, but we can kind of infer that from looking at these notches. To the right we see the same signal, but at a different location, 88 kilometers. And then we see that this first reflection is much shallower. So we can kind of get an impression that if we have had a lot of blue whale shots in this area, we could use this whale for seismic imaging. This paper created a lot of attention from the Independent to NRK in Norway, Newsweek, and even in Argentina, La Nación put this up. So that was quite exciting for us. We got more than 100 media attentions after this publication. To the left here, we see a summary of the data we did in 2020. So blue bars here, around 80, 70 kilometers here, is blue whales. And the green bars means just a downsweep, so we don't know for sure which animal or whale that is. So we measured around 830 whale calls during that 2 months period in 2020. So to the right here, you see how this looks like on an FX plot on the interrogator. So we can sit in Trondheim and look at this. So here we see a fin whale. It's around 20 hertz, this signal. And you see how it spreads out along the fiber at approximately 51 kilometers, as you see here. So it's fairly easy to observe this. And on this plot, we show fin whales. This is from the 2022 test. We see the 2 cables, and we see a timeline here at the top, which goes from 0, which is black, to 5 hours, which is white. And then red colors are around 2 hours, and yellow is around 4 hours. So here you see that we have followed several whales, annotated from A to H. So there are 8 whales here. And for instance, if we look at whale D, it starts here and go south and then go east and make a turn back again. So since we had 2 fiber optic cables here, we were able to kind of track these whales simultaneously for long periods. And the detection range in crossline is illustrated by this dashed white line here. So you see when the distance from the interrogator is increasing, this is narrowing. The beauty of this is that we can also estimate the direction of the whale, and we can estimate the velocity, which is around 2 meters per second in this case. And we can color code that again with the timing, as you see here. So it's a very useful tool for tracking whales. And again, I think we are one of the first to do this. Here it's how it looks like on the fiber. So here you see a whale at the end here, and then you see one whale at the middle, and you see how the signal is observed at both fibers, and you see it's stronger at the inner cable than the outer cable. And if you wait a bit, then you see that there is another whale here closer to Longyearbyen over here. So actually there are 3 whales vocalizing now at the same time, if you look at this image. So that is how this works. So it's quite easy to visualize how this works. We did a test with a known source because it's nice to know that we are able to track the whales, and therefore we asked the University of Bergen to go out with an air gun and a small vessel. And this is how the data looks like on the fiber, the inner cable here and the outer cable. And the vessel was sailing along the outer cable, the black cable, and then it turned and crossed over to the other cable. So if we look at the whale data for comparison, it looks very similar. Here we see three whales at three different locations, one at 60, 80, and 95 kilometers on the inner cable and the outer cable. So this is how our data looks like. And to the lower here, we see the spectrograms, etc. Then it's straightforward travel time inversion. We want to know the X, Y, and Z position of the whale. And then what we have measured is the travel time. And then, of course, we know the geometry. So apart from X, Y, and Z here, it's all data are given by the known fiber position. So in that way, we can formulate this as an inversion problem and estimate the position of the whale. Let's see. Yeah. So this is the test. The first test was to do this for the air gun. And on this plot, the correct position is the timeline, again, going from black to white for the vessel moving along here, similar to a whale. And then we see the gray dots is if you use a grid search method. And the blue dots is if you use a Bayes estimation type of estimation of the positions. And the two methods didn't differ much. And to the lower line here, you see the velocity estimates, but you also see the error between the exact positions given by the GPS position of the source vessel, and the maximum, the average error was around 100 meters in this test. So that was an accepted result, and then we used that to estimate the whale tracking. So this is an example of how this, when we did the Bayes estimation, we get this uncertainty ellipsis that you see here. So this is an example where the whale is stopping vocalizing, and you see when you do just extrapolation, the uncertainty ellipses start to increase, as you see in yellow now, and then the whale doesn't fit to that point, but it has moved over there. But since it's inside the uncertainty ellipse, we are still able to find the new location. So these are some of the challenges we meet when we do whale tracking. You have to kind of assume that the whale is not vocalizing at all times. This is an example of low frequency dust data, where we observe this is frequency now is from 0.01 to 0.15 hertz. And what you notice here is that these low frequency data over a period of 14-15 days, they show monotonic increase with time. You see these features that are increasing with time. And these features have been discussed by Walter Munk already in 1963. If you use the dispersion equation for water waves or gravity waves on water, you find this formula here, which x is the distance to the storm center, g is the gravity constant, and df dt is the slope of these features that we see here. So if you plug that directly into this formula that you see here, you will see, you can estimate the distance to a storm. So we have annotated them were 1, 2, 3, 4 here, and 1 is Edward from about 4,100 kilometers away, and 2 is a storm offshore Brazil in the period between 10th of July to 15th of July. So typically what you see in this data is that the low frequency signal from a storm enters 5 days earlier than the higher frequency here. So by looking at the slopes, you can kind of infer where this storm happened. You see also some yellow bands here, which are correlated to strong winds. For instance, here and also here, you see more. You have some of these yellow lines in the data. So this high quality or low frequency dust data is important because that can also be used for lunar gravitational wave detection, which is another project we are involved in. We go even further down to 10 to -5 in frequency. We can look at tidal effects, and what you see to the upper figure here, it's the measured tidal variation in Ny Ålesund. And in the middle, we see the estimates based on dust data. We have some gaps here, we lack data here and there. And if we plot this on top of each other, the red and the blue, you see that it fits very nicely with the periodicity, but also this long period thing that is following the moon's cycle is also captured relatively well, I would say. When you have strong winds, like at 20th of September here, you see that the dust data is out of range. It doesn't fit. So there are issues there. But it's quite impressive, I think, to see the similarity, the strong similarity between the dust data and the measured heights. Another example we have studied quite a lot is to study the shear wave resonance effects. I mentioned previously that we have some sediment, thicker sediment packages here, which gives resonance effects around 2-3 Hertz that you see here, these strong red areas. And then if we use earthquake in addition as a secondary source here, we see that this is actually this sediment thickness we can actually estimate based on this frequency. So when we make this fundamental frequency as a functional position here, we can find out the sediment thickness, how it varies along the whole path here. This is 60 kilometers long, and when we come over here to the right, we enter into basement. So it should go to infinity here. So it's quite interesting to see how the earthquake enhances the signal. And you see over harmonics here, like here, etc. So that's all. Then another example is from the Fjord bridge, which is a bridge not too far from Trondheim, 1 hour drive. It's a fairly new bridge. This was taken in February last year, so we see the fjord, which is salty, is covered by ice. And what we did was to install a fiber below the bridge. So we see that this gray thing below the bridge here, that's a room that is 4 by 3 meters. So we brought some students over there and they installed the fiber in 1 day in this gate that you see here. So the fiber is now not directly coupled to the concrete of the bridge, but it's coupled to this gate, electrical gate, that again is coupled to the bridge via these attachments here. This is the typical result. I show the bridge at the top here, and then you see the cars. Cars are weaker signals here, but trucks are strong signals. And you can estimate the velocity of the truck. You even see a shear wave event that is propagating here from one end of the bridge to the other. And you can use this to monitor cars, of course. If you look at this in the frequency domain without any load on the bridge, then you see this typical 2 Hertz resonance, which is the shear wave velocity of the concrete divided by twice the length of the bridge. But when you then put on more weight, like a truck, you see you excite a lot of frequencies higher. than 2 hertz. So this is things we are looking into now, and we have a cooperation here with the university in 2 universities in Germany, where we have acquired also geophone data to compare with this dust data. Then in 2021, we did a test together with Bane NOR, which is the owner of the railway system in Norway. And what we see here is, again, its distance along the horizontal axis, 23 to 40 kilometers away from Trondheim. And we see one train coming from Oslo here, and we see a local train coming from Trondheim. And the train from Oslo has to wait for this local train, and we see how that local train is going with a speed that is varying. So we see when it comes to the station here, it kind of has a very horizontal, vertical line almost, and then it's stopping here. And to the right here, you see cars driving on the road that is parallel to the railway. So you see a lot of cars here. We also see, if we compare this to a geologic map, the railway is now the black line here, and yellow areas is where you have a fluvial deposit from the river that is in light blue here. And the signal from the train is actually changing as you pass that when you go into the fluvial deposits here. So the blue here is clay. So when you have clay, it seems to be a narrower signal and less kind of reverberations in the signal. And when it comes over here, it seems to broaden. So you get a much more longer signal that is reverberating for a longer time, as you see here. So we haven't looked more into this, but we just observed that there is a change here, and maybe that's correlated with geology. That's what we think. This is a sensitivity test we did at the same occasion. This is the railway. So the fiber is here, 1 meter to the right of the railway. And you see a train that has passed here. You see that train on the upper right corner on the dust data here. And then we see me and the farmer who owns this land. We're jumping 10 meters away and 20 meters away. So you see that that was detectable on this fiber. Tells you something about the sensitivity. Then last May, we did urban monitoring in Oslo during the 17th of May parade. In Norway, that is an important date where children is walking in the streets with their flag, and where we have bands playing in between. So there is typically one band, and then there is a school, and then there is a new band, etc. So what we see here is we can estimate the step length of the children and the people in the bands, and you see that when the parade started at approximately 1 hour here, you get a very clean signal in the step length, and we see that it varies for almost 3 hours. So the parade typically lasts for 3 hours. So here you see the castle in Oslo, and you see the people walking up to the castle, and then they're turning around and coming back again. So this is a cooperation between Oslo municipality and CGF. So we actually monitored here for a bit more than a week. So what we see in the data is to the upper left here is we can estimate the velocity of the parade. It's around 1 meters per second, I think. 2. And then to the lower left here, you see an FX plot again, and you see that this typical frequency of a bit less than 2 hertz. That's typical for people walking in a pattern or an organized manner. And then you see when the parade stops around 4 hours here, it gets more diffuse. But when you have people walking in an organized manner, you see these clear frequencies, and you see the first and you see the second overharmonics at 4, 6 hertz, etc. You can make a simple model for this. And then this is how we estimate the average step length. It's given as the average velocity that we estimate from this upper left figure, and then this frequency that we see from these spectrograms or FX plots to the lower. And then if we compare this model to the smoothed data, we see that we get a fairly good fit at various locations, A, B, C, and D here, which is 1, 2, 3, 4 on this plot. We can even, if we look at the amplitude data here, it varies. So when you have a band that is playing, they are very organized. They go in an organized manner. So they get a very precise and strong frequency signal. So we can plot that as, if you plot the amplitude as a function of time, and then you see when you have this maxima, that corresponds to one band like you see on the figure to the right here. So there were, in this parade, there were in total 88 bands. And we were able to determine or observe 83 of them, as you see on the picks that we have done here in an automatic picking. And then the green arrows show candidates for which one we have missed by the, and the red one is one that we are very uncertain on. So it seems to be a very good correlation between the amplitude and these bands that are. And in the middle here, there are children going in a more disorganized manner than the bands. So that's why we have this variation in signal. I think this is the last example. It's from together with a power supplier in Lofoten, which is far north in Norway. So it's a stretch of approximately 100 kilometers. So here the fiber is actually in air. It's 10 meters above surface. And some places it's crossing sea and then it's buried in the sea. So what you see to the upper right here is the data on a windy day, 9 to 15 meters per second. And when you have the low, the bluish areas here, it's when it's either when it's buried in the ground, like here, or Gimsøystrømmen, that is when it is in sea, when it crosses the sea. And then when you see the next day, 12th of January, it's less windy, and then you see it's less signal on the fiber. So then the question is, can we use this to monitor wind? And this is a movie showing the big red arrow in the middle is proportional to the wind strength, and you see also the direction. And then you see the fiber when it picks up signals that we interpret to be caused by the wind. So now the wind is around 2 meters per second, and you see that it influences the fiber at some locations. And when the wind is increasing, and now it's decreasing again, so you see hardly any signal. And now the direction is also changing. Now it's a bit stronger, 2.2. And you will see that when the wind becomes stronger and stronger, we can measure it at more locations along this fiber optic cable. There is a mountain here where the fiber is crossing. So there's like a mountain pass. You see the red signal there now. That is a critical point where we really like to see and how much the wind is kind of influencing the cables. also the power cables, of course. So we think this is a nice possibility to calibrate this to wind data and to use it for meteorological purposes also. So it's a bit long, this movie, but I think we will see that the wind is, we are 35 hours. It's still fairly weak, but it's now picking up, I think. So the idea is then to try to calibrate. Now you see it's stronger winds, and you see that the mountain is kind of shadowing. There is a shadow effect. So it's weaker where the fiber is behind the mountain for this wind direction. And now it's very strong wind, and you see it's red almost along the whole fiber. And then in the mountain pass, you see it's dark, it's black. Then it's strongly influenced by the wind up there. So this is something that is under development, and where we are going to do more testing and compare directly with wind measurements. Yeah. So I think I stop there, and if you have questions, I'm ready to answer. Thank you.
Thank you very much, Professor Landro. I'll read out some of the questions, but a reminder, if anybody has any questions, to post them in the Q&A box, not the discussion box. So with that, I'll ask one of the first questions is from Andres Chavaria, asking about the Svalbard cables, the installation of them. I think you did mention that they were trenched. That was part of the question, but also what depth that they were trenched at, and the diameters of the cables and the number of fibers within, if that information is easily available.
Yeah, the diameter of the cable is around a bit less than 1 inch. The depth is approximately 1 meter below seabed. So it was trenched by a big flow that was at the seabed. And what was the third? It was about the number of fibers. It's there are quite a lot of fibers in there, so it's easy for us to get access to dark fibers that are not used for communication at the same time. So it's the number I don't remember, but it's sufficient.
Very good. Is multiple fibers a necessary requirement, or is a single fiber enough for this kind of exercise?
It's necessary to have what we call the dark fiber that is not used for telecommunication. But yes, in the center, SICT and ASN are now testing if they can exploit the L-band. For communication, we use the C-band in the fiber. So there is a possibility that this L-band can be used for sensing, while you use the C-band for communication. And they are now testing how much crosstalk you might have. And so far, the test seems very promising.
Oh, excellent. So that could expand the application. We have an anonymous question asking about asking if you could expand on expand a bit on the estimating of sediment thickness from resonant frequencies. And the extension part of the question is, how do you know that variation in sediment thickness is what's causing the observed pattern? Can you model this phenomena? And I'd even go further as to ask if there was any kind of calibration done.
Yeah, so in the paper we are submitting now, we are comparing this to high resolution data that was acquired by the University of Tromsø back in 2011. So there we pretty much can see the thickness of the sediment column from this high resolution data, and by doing that we can now have a grip on how to interpret and how to make it more plausible that this is what we see. Again, the effect of Shaver resonance was discussed in early days by Godin and several. So that's not a new thing. It's the application that is new.
I see. I do recall in one plot that you showed that there was an absence of your resonance sediment thickness where you knew that was basement outcrop.
Yeah.
I guess that's some form of calibration.
Yes, that's also a way to. But it's when you compare to this detailed high frequency shallow seismic data, then you get more convinced when you see that comparison.
Fair enough. I have another question from Thor Garden asking about the DAS temperature measurements that you were making. The question is, what is the temporal and spatial sampling? Is it distinctly different from DTS in that respect?
It's the temporal sampling we used, that Nick and Kjetil used, was quite high. It was on the millisecond level, and then you smooth that and you low pass filter that, and you do a median filtering first of all. So it's a bit of filtering that is necessary to make the comparison to the DTS. The sampling for the DTS, I don't remember. Yeah.
Well, I guess at millisecond level, it must be fairly narrow.
Yeah.
Excellent. We have a question here from Per Bach asking about the monitored signal P waves. Are the monitored signal P waves or Rayleigh waves? Are the monitored? Okay, it's kind of a repeated question. Yeah, he's asking about the difference between the signals you're detecting. Are they P waves or Rayleigh waves?
Both. We observe for the earthquake data, we observe the P wave. For the data in Rissa, for instance, when we use the hammer shots, then it's a surface wave definitely. So it's the shear wave velocity we infer from that, and then we have a polarity reversal at zero offset. So if you have shear waves, you always see a polarity reversal. If it's clean P waves, we never see that. So it's fairly easy to distinguish between P and S waves / shot waves or surface waves. So that's yeah.
Okay, very good. We have a question from Florian Belebinhaus, I believe I've said that correctly, asking about the storm data you were showing and asking why does it take 5 days for the signal to travel? Are these not the microseismic events, but actual ocean waves causing the signal?
Yes, that's correct. I forgot to say that, I think, but this is actually, it's ocean waves that are traveling by the speed of maybe 200 meters per second or 200 kilometers per hour. So it's not very high speed waves, so they take some time. So the low frequency, when it's say 13,000 kilometers to travel, it simply takes several days between the low frequency part, which has a higher velocity, than the high frequency part of such a gravity wave or ocean wave. So that's the main reason. So it's quite interesting. I think it's quite fascinating. But as I said, this was discovered and published by Walter Munk already in 1963 using seismometer data.
Fair enough. Okay, we have a question from Sanjay asking, do you do DAS, or can you do DAS fiber optic sensor analysis by using wavelet transform?
Why not? Like it's like, because this is like as I see it, it's like conventional seismic streamer or array that is long. It has some differences, especially on the zero offset. It is weaker, of course, if you look on the P wave. Shear wave is stronger at zero offset, and so the same techniques as we are using in conventional seismic is more or less applicable. But of course, when you do the processing, or such as I showed one example of processing, that of course you need to take care, because you have less zero offset information that is normal in conventional seismic processing. But it's essentially the same. You have an array that is 100 kilometers long.
Quite a lot of data. We have one final question, perhaps from Majid Beraki, asking, is there any comparison in the 3D sense against nodes and the fiber data? I guess that's tricky to answer since this is kind of a 2D application.
Yeah. That's a very interesting question, and we have actually started to taste or to look at that because we have these two streamers on Svalbard, which is varying. So we have a crossline separation of 3-4 kilometers. So we can do like a, I would call it 2.5D maybe test, where we have some crossline information, and we have some seismic shots there. So, but we haven't really done that yet. But it's a very good question, and it's interesting to see how especially for this CO2 monitoring, if we have, let's say, a spiral or any kind of more random configuration, how far can we stretch this towards a more complete 3D imaging? So the answer is that we don't know yet.
Okay, well, something to look forward to, and perhaps a way forward for the future as well. Well, thank you very much, Professor Landro. I'm sure everybody in our audience would join me, and thank you for a wonderful presentation. Very, very interesting subject that probably will see a lot more development in the future. Very, very interesting applications. So with that, on behalf of the European RAC for the SEG, Laurie, whose indispensable help puts these things together, we thank you very much and look forward to hearing from you again.
Thank you. Bye-bye.
Thank you, Professor Landro.